Hi there. Today we're going to do section 5.2, and that'll finish up chapter 5 for us. So it's pretty much the same as what we did in 5.1. It's a lot shorter of a section, obviously, because we don't have to do as much background information. So this one will be pretty quick. It's not an hour long like the last one was. So let's get started. So it's the same theoretical background as what we had in the previous section. And what we saw last section was that the randomization distributions and bootstrap distributions are normally distributed. And then we use the normal distribution to find p-values. So what we're going to do is the exact same thing, except we're going to focus only on the bootstrap distributions. And we're going to see that most of the stuff you saw in chapter 3 when you did bootstrapping was in fact bell-shaped, and we can replace bell-shaped distributions with a normal distribution. So the idea here is that we're going to try to find confidence intervals. And when we did bootstrapping, we had a dot plot, and we would capture the middle 95% or whatever the number was, of the bootstrap statistics. So the equivalent idea here then is that we want to find the interval that captures the middle 95% of the area in the normal distribution. So it's really the same thing we did in chapter 3, except instead of dot plots, we're going to be replacing those dot plots with smooth curves. And we have to introduce one new concept. This is really the only main vocab term that we use in this section, and it's called a critical value. So we need to find the endpoints of the confidence interval. When we do that, we use what's called the inverse normal value. The inverse normal value is what we call the critical value, and we just call it Z star. On the previous slide, the critical value for a 95% confidence interval is 1.96. So let's go back to this slide and let's look at this. So if we have a theoretical normal distribution here and we select the middle 95% of the area, right? So 95% of the size of the region under the curve is here. So this is 2.5%, this is 2.5%. Well, StatKey and your graphing calculator can easily return the calculation for what these numbers are. If any of you have taken a stats course 10 or more years ago, and this is like your second take at it, typically or historically, these Z-critical, and what we will learn are T-criticals later, these values were given on tables, and they were very hard to read, and you had to carry these like reference sheets of paper around. It is much easier to use a graphing calculator. Oh yeah, one more thing. So you can see that what we called the 95% rule is in fact 1.96 on either side. There are some cases when it is 2, but for a normal distribution, it's 1.96. So you can see why we just rounded that to -2 and 2 earlier in the class when we were doing 95% rule. But the exact value is 1.96. And so that's what we call the Z star, or sometimes it's called Z critical or just critical value. They all mean the same thing. And it's the inverse normal value for the tails. So what you have to do in StatKey, it's real easy, right? It's what you did in chapter 3. But on a graphing calculator, finding those Z star values is a little bit tougher. So when I do the examples, we're actually going to break that into 2 different examples, just so I don't have to keep switching screens so much, because it's a lot different. So we're going to talk about StatKey first. We're going to see how to do, like if you need to solve a problem like this on the homework, you're allowed to use your calculator, but if the problem says use StatKey, go ahead and use it. On a test, you're going to have to use a calculator. So I'm going to go over all this. So this is just a slide for your reference. So let's go ahead and do this first problem. So what we want to do is find the endpoints of these confidence intervals. So we have a 96% confidence interval for a correlation and a 78% confidence interval for a difference in means. What we saw in chapters 3 and 4 is that it didn't matter what the sample statistic was. It didn't matter what the parameter was in terms of like how you evaluated a confidence interval. Because the bootstrapping used the data to build a distribution, and then you just chose the middle p% of the data. Here we're using the standard normal distribution. So all we have to do is select the appropriate size of the region. So let's go ahead and do that. All right. So again, I'm going here to theoretical distributions, normal. That's the same place we went in section 5.1. And as you can see, it gives you the default setting here is mean of 0, standard deviation 1, which is what we want. We're doing confidence intervals, so clearly we're doing two-tail. And then all you have to do is change this number. So the first one we're doing is 0.96. So you can see that we have two numbers at the bottom. One of them's positive, one of them's negative. We just pick, it really doesn't matter which one you pick. Just when you write it down, it's positive. If you pick the one on the left, the critical value, it can be negative, but there's no reason to make it negative. So just, if you look over here on the left, and it says negative 2.054, then just write down 2.054. It doesn't matter which one you pick. The graphing calculator will give you one or the other. StatKey gives you both, so it doesn't matter which one you pick. Then the other one we wanted to do was a 78% confidence interval, here part B. Notice that I don't care what it is, what the parameter is. It doesn't affect the calculation. You just type 0.78, and you're done. 1.227 and negative 1.227. So that's all you have to do in StatKey for finding these t critical values. Sorry, z critical values. We're doing t critical values later, but for right now it's z critical. And that's all you have to do. All right, so that was that problem. And there's the answers. Obviously, make sure you can do this. So if you want to pause and try both of these on your own, go ahead and do that. Now we want to see what to do on a graphing calculator. Again, it's a lot different. You can see that horrible, ugly formula there. Don't worry about it. I'll show you how to use it. And the book does not do a good job of explaining this. So you should really, really just follow the way I'm going to show you to do it. You absolutely must use this method on an exam. So please practice what I'm showing you how to do. So the way that this works, let me go ahead and get this calculator rolling. Is it on? Yep, there it goes. Okay. If we go back and look at this graph, let's say for the sake of argument that I want to find the critical value here. So the way this works is here's how to do it on the calculator. So when we did section 5.1, we used normal CDF, right? So it's still second vars. Normal CDF here, this is what we used for section 5.1. We're just going one underneath it to inverse norm. Notice we have area, mu, sigma, right? However, when it says area, it means area to the left of the endpoint. You have to put in the area to the left. If you put in anything else, you will get it wrong. Well, the area to the left of the endpoint is what we called the percentile back in chapter 2. And we also did percentiles in chapter 3, right? When we did confidence intervals using percentiles. So what you have to do then is figure out how to use this formula, right? Notice we're already in inverse norm. The first thing you have to type in is 1 minus alpha over 2, and then 0, 1. The 0, 1 are already given, so you just need to figure out the area to the left. And then look at this setup. So there's two different formulas here. Once you figure out how this works, it's not bad. If for some reason you're struggling with it, just follow what I'm about to show you. Okay, so let's say that we're going to do this one. Well, think about what StatKey is telling us. 96% is in the middle. So that's 2% here and 2% here. You have to type in the area to the left of the endpoint. So you have two options. You either look for this endpoint or look for this one. it's a lot easier to look for the left endpoint. A lot. I know you're thinking, well, this formula doesn't look easy, but trust me on this. Well, StatKey tells us that 2% is to the left. So for here, I would just type 0.02. Just got to hit enter a bunch of times. And you get negative 2.054. So even though it's a minus value, just put in the positive number. Again, it's not wrong if you write a negative down, but the online homework might not accept it. The quizzes might not accept it. And you don't want to always have to open StatKey to find the area to the left. So let's do this same problem again with the formula. Oop, hit the wrong button. Let's try it again. Oh my gosh. Hold on, I gotta get out of here. Oop. I can't even read the buttons on the screen. Here we go. There we go. Okay. So let's use the formula. Notice it says 1 minus alpha over 2, where alpha is 100% minus the confidence level. So if we're doing a 96% confidence interval, then alpha is 4%, right? Because 100% minus 96% is 4%. So here, just type in 1 minus 0.04 divided by 2. That's the way I would recommend doing it. Right? And if you do it this way, you get the area to the right. Notice it's positive. So it's up to you how you want to do it. You can either take the confidence level, split it in half. Take the confidence level, find the tails, and just take the left tail, and you get a negative number. Or you can use the formula and get a positive number. It's up to you how you do it. But anyway, obviously, this number here is 0.98. So you're either finding 2% to the left or 98% to the left. If you have questions about this, make sure you ask during the next class, because you're going to have to be able to do this on a test. All right, so let's do some of these. So let's go ahead and just do these live on the calculator. I'm not going to be sketching the normal distribution for these particular problems just to make this video not an hour long. You should be able to do that, though. Everything's going to look like a confidence interval. Just make sure that you're estimating the size of the area under the curve correctly. So let's do an 80% confidence interval for proportion. So think about it. How much is on the left side? If 80% is in the middle, how much is on the left? Or if you want to use the formula, that's fine too. So I'm going to go ahead and use the formula. So 100% minus 80% is 20%, so that's 0.2. So I type in 1 minus 0.2 divided by 2, and you get 1.28. Right? So that's exactly what I just typed in. I highly recommend that this is how you do it. Again, if you're very, very good at this stuff, you can use, and you can do it in your head, fine. You don't have to show the work for where that alpha value comes from, for where the area value comes from. You don't have to show the work on that or anything. Let's do the next one then. Oop. Same thing here, 94% confidence interval. Well, 100% minus 94% is 6%, so I'm just going to type 0.06 in here. And everything's happy. Oop. Now, I know it's hard to kind of see this stuff as you type it in, but the way that the calculator does it, just understand that it's the same numbers in order. So you can see like the calculation here, but then it's just 0 and 1 after that. The calculator won't show everything at once for whatever reason. So these are Z critical values, and you use them to build confidence intervals without using StatKey. You're allowed to use StatKey, but on a test, you must do it this way. So the only question then might be, how exactly do we get to this critical value? Like, why is this needed? Well, remember that we can overlay this distribution with a smooth normal distribution. And in chapter 3, when we built confidence intervals, we had a standard error that we used when we did 95% confidence intervals. After that, we just used percentiles, as you may recall. So this is a percentiles method, what we're using here. So we really don't need the standard error. And even if we do have the standard error, you can still use it, which is what we're going to be doing later. I'll show you how to do that here in a second. So if we have a bell-shaped distribution, a p% confidence interval can be found as the interval containing the middle p% of a normal distribution. So what we're doing is we're using the z-critical. We're finding that using percentiles, and then we're going to use the standard error given by the bootstrap distribution. So we're kind of mixing the two techniques that we did in chapter 3. Whereas what we just did in the last section pretty much looked exactly like what we did in chapter 4. This is sort of a hybrid method that we never used much. We used it for 95% confidence intervals, but we didn't know what a critical value was in chapter 3, so we didn't use it. We just used percentiles. So here we're using percentiles and then moving everything over into the standard normal distribution, which gives us the z-critical values. So it turns out that if the bootstrap distribution follows a normal distribution with a given standard error, we find the confidence interval using this formula. So this should look really familiar, right? Confidence intervals are centered at the sample statistic. The variability is given by the standard error. And in chapter 3, if we did a 95% confidence interval, we just said that what we're calling z star now was just the number 2. But now we can build any size confidence interval because we're using percentiles to find the z star values. So that's really kind of the missing piece. And that's one reason why in chapter 5 we do confidence intervals second, because the technique doesn't look exactly like what we did in chapter 3. So there's your formula. That's just a generic formula, and we're going to use that the rest of the semester. And don't worry, you'll have plenty of formulas by the end of the class. You won't be wishing you had more, believe me. So let's go ahead and do one of these. Assume the standard error comes from a bootstrap distribution that is approximately normally distributed. So if we needed to, we could go into StatKey and build a bootstrap distribution and then take the standard error from that. But these problems are all designed in such a way that the standard error will just be given to you. So we're going to find a 95% confidence interval for a proportion p if the sample has n equals 300, p hat 0.43, and the standard error is 0.03. So you always find the z star value first. So let's do that. So what am I going to put here? What number am I going to put here? We're doing a 95% confidence interval. So what number do I put here? We'll just go through it the way that I went through it in example 2. 100% minus 95% is 5%. So I'm just going to put 0.05 here, and then I'm just going to leave it. The calculator does the rest. And it shouldn't be a surprise that we get 1.960. This was actually from one of the earlier problems that we did. So there you go, 1.960, because I'm rounding to 3 decimal places. Now I use the formula, and I just plug everything in. So my sample statistic is p hat, so 0.43. Notice it says plus or minus. It doesn't matter which one you do first. I'm going to go ahead and do minus first because it's going to be a smaller number, so the order it comes out is the order I'm going to write it down. My z critical value is 1.960. I'm going to multiply that by the standard error, 0.03. And then I'm going to do this again. Oh, hit the wrong button. And I'm just going to change this to a plus. Right, so we got 1.96, and then just use the formula. And again, final answers are rounded to 3 decimal places. So it would be 0.371 and 0.489. So this is the way that we do confidence intervals in this section. So go ahead, if you want, pause the video, try this problem again just to make sure you can do it all the way through. But what we're going to do now, before we get into more examples, is obviously we're going to do a lot of 95% confidence intervals. Well, that means Z critical is always 1.96. So this is a number that you should just remember. In fact, there are 3 very common confidence intervals, right? 90, 95, and 99. And you can very easily check that these are the Z critical values. If you want to do that now, pause the video and do it on your own. But they are standard and they are used a lot. So I do recommend memorizing this table. You will be given these values on an exam, but just to make your life easier, because you see this stuff so much, go ahead and memorize them. You'll see it over and over and over again. So from this point forward in the video, we're assuming these are known values. All right, so let's just go ahead and do just some like practice problems, just so you can get the hang of it. If you want to try it on your own, go ahead and pause the video here. Try it on your own, and then you can check your answers after we go through it. So we have a 90% confidence interval for a mean. The sample is 80, X bar is 23, S is 5.9, standard error 0.66. All right. Well, again, pause it if you want to try it. So I'm just going to go ahead and do it because I already know what Z star is for 90%. I already know it's 1.645. There's the sample statistic. There's the standard error, and we're done. So as you can see, this is going to be very, very simple once you get the hang of it, right? So sample statistic. Again, I'm doing the minus part first. It doesn't matter which part you do first. And then 1.645 times 0.66. And then I'm going to do it again, just with a plus. Again, don't forget to round. 3 decimal places. You just follow the homework for what you're supposed to round. So take a sec and double check that answer, and I'm going to drink some coffee real fast. Alrighty. So there you go. And this is really indicative of the type of thing you're going to see on a test. And the homework looks like this too. In fact, I think examples 4, 5, and 6 are all homework problems. So if you're thinking, oh man, this is way easier than p-values, it is. The only thing that you have to work at is that Z star. But if it's a common confidence level, like 90 or 95%, you just remember Z star. If it's some strange one like 94%, then you have to compute it from scratch. Don't memorize all of them. There's too many. All right, let's do, so now we're going to keep expanding it out, right? We're going to keep adding the new techniques to problems that look like things we've done before. A recent study found that of the 1,771 participants aged 12 to 19 in the National Health and Nutrition Examination Survey, 345 had some hearing loss, defined as a loss of 15 decibels in at least one ear. The sample size is large enough to use the normal distribution, and a bootstrap distribution shows that the standard error for the proportion is 0.009. All right, so what is our sample statistic? Pause the video if you want to think about it. Well, we can see that there's a whole bunch of numbers here, right? Numbers, 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 right? What numbers matter? Well, this is clearly the sample size. This is just an age range, so this is part of the population. This is 15 decibels, so that's part of the variable, right? They're measuring if each person had loss or didn't have hearing loss. They're not measuring how much the hearing loss was. They're turning a quantitative variable into a categorical variable. And there's only one population, and there's only one sample, so it's a single proportion. So the sample statistic will be p hat. Now you just have to figure out where to find it. Well, we know the denominator of p hat is always the sample size. Well, the only other number in the study that we're given is the 345. So p hat is going to be 345 divided by 1771. Right? So that's p hat. Now it says find and interpret a 99% confidence interval for the proportion of teenagers with some hearing loss. So we use the generic formula. The formula is sample statistic plus or minus z star times the standard error. We're given the standard error. It's a 99% confidence interval. So from the table, or if you want to compute it on your own, you can. From the table, we get 2.576 for our z star. And we just plug everything in. So 0.194. Again, rounding everything to 3 decimal places. Oh, 0.195. Minus 2.576 times the standard error, 0.009. And you do it again for the positive part, right? So 0.172. Do it again for the positive numbers. Just change this minus to a plus. And you get 0.218. So there you go. And then make sure you interpret it correctly, right? We're 99% sure the proportion of all teenagers with some hearing loss is between 0.172 and 0.218. So looks just like a problem that we would do from earlier in the semester, for sure. But no messy bootstrap distributions, right? In Chapter 6, we will see how to compute the standard error for a problem like this. But for right now, it's given. All right, one more problem, and then we're done. A survey conducted in July 2015 asked a random sample of American adults whether they had ever used online dating, either an online dating site or a dating app on their cell phone. The survey also asked participants for their level of education, and we wish to estimate the difference in the proportion to use online dating between those with a college degree and those with a high school degree or less. Well, we have the data, right? So you can see, how this data was collected, right? So we have kind of a big sample, right? 1,458. We can also see clearly that there are 2 categorical variables. That means that our sample statistic will be a difference in proportions. So it's going to be a p hat 1 minus p hat 2 for the sample statistic. In this case, I'm just going to call it p hat c and p hat h because the explanatory variable here is the columns, right? And the idea is, can you make a prediction about whether somebody uses online dating based on their education level? That's sort of the way the study's designed. Again, we're given the standard error. We're going to find a 95% confidence interval. So really all we need is the sample statistic, right? Well, we know it's p hat 1 minus p hat 2, so it's proportion of college-educated folks who use online dating minus the proportion of high school or less educated folks. And we're just looking at the yes answer, right? So it's going to be 157 out of 823. If you guys want to use the stacked fractions, I remember for this kind of stuff, you might want to use the stacked fractions. It's up to you. I don't care how you type it in. But I just like showing different ways. So 157, 823. Later on, when we get to Chapter 6, some of these problems get sufficiently complicated that typing it in a certain way so it looks a certain way really helps you kind of like check whether you've done it correctly. I had a 635. Right? So that's p hat c, that's p hat h. And we're going to round it to 3 decimal places, of course, right? So we get 0.081. And we're using the generic formula for the confidence interval. So it's sample statistic plus or minus. So I'm just going to do minus first. Z star, this is a 95% confidence interval, so Z star is 1.96 times the standard error, right here, 0.019. And then we just do it again with a plus. And there you go. Now, this particular question has a follow-up portion. And the follow-up portion here says, if you want to get caught up, just pause the video, but I'm going to keep rolling on through it. Hit the wrong button. For part C here, is it plausible there's no difference between the population proportions? Explain using your answer from part B. Well, we can be 95% sure that the difference in the proportions is between these two numbers. Right? So, it's not believable there's no difference between the proportions because 0 is not in the interval. This is a little typo here. I'll fix this before I post it. But look at these numbers here, because these are the ones we just computed. So 0.044 to 0.118. The confidence interval contains only positive values. That means that the proportion of college-educated folks to use online dating is in fact higher in the population than the population of high school-educated folks to use online dating. So if these are all positive numbers, that means one of the populations is in fact higher. What we saw earlier in the class were a lot of questions about, is there a difference or not? Well, we're just revisiting what we did in Chapter 3. So that's sort of how you interpret those questions in Chapter 3. Right? You had a problem on the exam that looked similar to this, right? I gave you a confidence interval and said, what can we say about the populations? So this is the same stuff you've been doing since Chapter 3. All right, well, that's it for this problem. And if you have any questions, you can reach out to me by email, come to tutoring, or stay after class, or come early to class. And that's it for Chapter 5. You can go, once you've finished the homework for this, you can go ahead and do the next adaptive quiz, and next video will be Chapter 6. So have a good day, and I'll see you next video. Bye-bye now.